The next topic is mutual induction. See, what do you mean by mutual induction? Mutual induction means if you have two coils, so this is coil C1 and this coil C1 is connected to a cell through a key. And then you have another coil C2 C2 is connected through a galvanometer. So if I change magnetic field in coil 1 or if I change current in coil 1, then some EMF will induce in coil 2. I'm changing current in 1 and EMF will induce in 2. This is known as mutual induction. I'm changing here and the effect in this second coil. That's mutual induction. So as soon as I close this key, the current in the first coil will increase. So due to increase in current in the first coil, a current will induced in the second coil. This is what we call mutual induction. This is known as mutual induction. So why it happens? Why a current increasing in one coil will induce a current in the second coil? It's basically due to change in magnetic flux. See, if a current is passing through this coil C1, then this coil C1 will generate some magnetic field. The coil C1 will generate some magnetic field. Some magnetic flux will link with this coil C2. So this C1 will generate some magnetic field. Due to that magnetic field, a flux is linked with the coil C2. And if this current is increasing, then the magnetic field due to C1 will increase, flux through C2 will increase, and due to that increase in flux, a current will induce in C2. So is it clear? Jubana and Afroza. Is it clear? Mutual induction. I'm changing current in one coil and EMF is inducing in the another. This is known as mutual induction. Okay. So you can define it as it is the phenomena of production due to which EMF induce in one coil due to change of current in neighboring coil. Due to change of current in neighboring coil. So if you are changing current in one coil, then EMF will induce in second coil. This is known as mutual induction. Now, the mathematical steps involved are flux linked with coil 2, If there are more than 2 coils, then we will consider mutual induction in pairs. If you have 3 coils, then you will consider mutual induction in pairs. Due to this coil in this coil, due to this coil in this coil. You can't have mutual induction due to simultaneously for 3 coils. You will take pair of 2 coils. So now, if I define flux phi2 is flux linked with coil 2. Linked with coil 2. And I1 is current through coil 1. Current through coil 1. So the flux linked with coil 2 is proportional to the current in coil 1. Phi 2 is proportional to I1. Now, if I remove the sign of this proportionality, then phi 2 will be equal to Mi1. This M is known as coefficient of mutual induction. So EMF is inducing in coil 2 due to coil 1. So I write this as M21. So M21 means its coefficient of mutual induction of coil 2 due to coil 1. So the coefficient of mutual induction of coil 2 due to coil 1 is M21. So phi 2 is its M21 I1. So if you are changing current in coil 1, then flux linked with coil 2 will change. Now, using Faraday's law, we can calculate induced EMF. Using Faraday's law, you can write that your induced EMF E is minus of d over dt of phi. Or in general, I'm writing this as phi is equal to Mi. Because current can flow through any of the coil. Maybe current is flowing through I2, and due to that change in current, some EMF will induce in coil 1. So in general, I'm writing phi is equal to Mi. So induced EMF will be minus of d phi over dt. This is Faraday's law. So I can write this as, this is minus of d over dt of Mi. You can take this m outside the derivative because the constant, it's minus m di over dt. So this is your induced EMF. That induced EMF E is minus of m di over dt. This negative sign here will represent Lenz's law. That induced EMF will oppose its cause. That's Lenz's law. From here, we can even calculate the unit of M. So if I take just magnitude of E, then that is M di over dt. I'm not using this negative sign. I'm not considering the direction of EMF or current. So I'm just putting the mod over here. So from here, you can write that your di over dt, rate of change of, you can write that your M is its modulus of EMF over di over dt. M is di over dt. So you can write SI unit here, that SI unit of M, the SI unit of EMF is volt, di over dt is ampere by time, that's ampere per second. So you can write this as it's volt per ampere seconds. And this you can write as Henry. So SI unit of mutual induction is basically Henry. That's the SI unit. Now on mutual induction, you can get some conceptual questions. Questions like, on what factors does mutual induction of two coils depends? So mutual induction mutual induction of two coils depends on first part. It depends upon number of turns in the coil. Second, it depends upon the separation between the coil. After separation, it depends upon the orientation of the coil, how those two coils are placed. Relative orientation of coils. And also on the medium. It also depends upon the medium between the two coils. These are the factors which can affect mutual induction of two coils. Okay, solve this question, formula based numerical. An EMF you need mutual inductance of these two coils. See, you can use this relation here, like E is minus of M, it's di over dt. Instead of di, you can write delta I over delta t. So E is 0.5. For delta I, you can take change in current. Initial current is this, final is this. You can calculate the change in current, and the time interval is this, milliseconds. So 1 millisecond is basically 10 raised to the power minus 3 seconds. See here, E is 0.5 volt. Delta I, change in current is final current minus initial current. I2 is 2, I1 is 5. So delta I is minus of 3 amp. Time taken is 300 milliseconds. So it's 300 into 10 raised to the power minus 3. So delta T is 0.36. Afroza, did you get any answer? So if I substitute all values here, then your E is 0.5 with a negative sign. M, delta I is minus 3, delta T is 0.3. So negative negative is positive. 0.5 is M by 0.1. So M is 0.5 into 0.1. So M comes out to be 0.05 Henry. The next is you're supposed to calculate mutual induction. Next, you need mutual induction of two long coaxial solenoid. So it's mutual induction of two long coaxial solenoids. So in this derivation, I will use few concepts of magnetics. The first one was if you have a solenoid, then magnetic field of solenoid is mu naught Ni, where N is the number of turns per unit length and I is the current through the solenoid. And one more thing, if you have a solenoid, then magnetic field is confined only within the solenoid. There is no magnetic field outside the solenoid. This also we have discussed that as compared to outside the solenoid, magnetic field is weak. So you can say that outside magnetic field is almost zero. So next is mutual induction of two long coaxial solenoids. So I'm taking two coaxial solenoids, like this is solenoid 1. This is solenoid number 1. This is S1. The radius of the solenoid S1 is R. After this S1, you have another solenoid, that's S2. This is solenoid S2. So the radius of S2 is R2. This is S2. S2 is the outer one. So this is solenoid S2. The radius of the solenoid S2 is R2. And the radius of solenoid S1 is R. So you have two solenoids, they are wound over the same axis. The radius of S2 is greater than that of S1. Now you're supposed to calculate mutual induction of these two solenoids. So first of all, I'm calculating M12. When I'm calculating M12, that means it's mutual induction. It's mutual induction of solenoid S1 due to or with respect to S2. S1 with respect to S2. S1 with respect to S2 means you are passing current through solenoid S1. You're passing some current I1 through solenoid S1 and EMF will induced in S2. When I say mutual induction of S1 with respect to S2, that simply means I'm passing current through S1 and EMF will induce in S2. Fatma, you are just a bit late. We have started mutual induction. The working formula here is phi is equal to EMI. That's it. Where phi is flux, M is a constant coefficient of mutual induction, and I is the current. So you haven't missed much. You just have missed a very small topic. What is mutual induction? That's it. So I'm passing current through solenoid 1, that's I1. EMF will induce in solenoid 2, that's S2. Next, we have few terms like N1, number of turns per unit length, number of turns per unit length in solenoid S1. Then you have N2, which are number of turns per unit length in solenoid S2. L is the length of both the solenoids is same. L is length of solenoid S1 and S2. Similarly, R1 and R2 are radii. R1 is radius of S1 and R2 is radius of S2. So to calculate mutual induction, M12, we are calculating M12, right? So first I will calculate M12 or M21, just let me see. Yes, first of all, I will calculate M12, then we will calculate M2. So for M12, current will pass through the outer coil S2 and EMF will induce in the inner one, that's S1. So I need magnetic field so current I2 will pass through S2. M12 is when there is EMF induced in S2, right? No, Jabana. M12 means when EMF is induced in first coil due to second coil. Means current is passing through the second coil and EMF is in first coil. When you are writing M21, EMF is induced in second coil due to first coil. Means current is through first coil and EMF is in second coil. So when current I2 will pass through the second coil, then second coil will definitely generate some magnetic field. So magnetic field due to S2. Magnetic field due to S2. So magnetic field due to S2 will be B2, which is mu naught N2 I2. I call this as equation number 1. So due to this magnetic field, so if I draw this here, I'm drawing the top view. Means if you look at this solenoid from this side, when you look at this solenoid from this side, then you will see that there is a solenoid S2 circular, and inside that solenoid S2 you have another solenoid which is S1. That's S1 and this is S2. When you're passing current through S2, then this S2 will generate some magnetic field. Throughout inside S2 you will have some magnetic field. So this B2 is mu naught N2 I2. Next, you can calculate flux linked with each turn of S1. So flux linked with each turn of S1 is phi 1 prime. And how you calculate flux? You take magnetic field of B2 and multiply it by area of S1. So that is B2 multiplied by pi R1 square. That is equation number 2. Now this is with each turn. Now I need total number of turns in solenoid S1. Total number of turns in S1. That I represent by capital N. So to calculate total number of turns, you can simply multiply number of turns per unit length by the length of solenoid. Number of turns per unit length is N1. The length of the solenoid is L. So just multiply this N1 with L. This is equation number 3. That's number of turns per unit length. This is total length. So that's total number of turns in this one. So flux linked with, this is flux linked with one turn of S1. Now I need total flux linked with S1. Total flux linked with S1, which is phi 1. Phi 1 is N1 into phi 1 prime. So you can write your phi 1 as N1, which is N1L, multiplied by phi 1 prime, which is B2 pi R1 square. That's equation number 4, right? I need total flux linked with S1. So the total flux linked with S1 is total number of turns in S1 multiplied by flux per unit length. So that's N1L into B2 pi R1 square. This is total number of turns multiplied by flux with each turn. So that's total flux. So this is B2 pi R1 square N1L. That is equation number 5. Next, I can substitute the value of B2 from equation number 1. The next step, I can substitute this 2 in 1, 1 in 5. So if I substitute 1 in 5, then I will get that phi 1 is B2, which is mu naught N2 I2 multiplied by pi R1 square N1. So the phi 1 comes out to be mu naught N1 N2 pi R1 square Li. That's equation number 6. Now we have flux which is mu naught N1 N2 pi R1 square Li2. So this is the total flux which is linked with the solenoid S1. Now if I say that M12 is mutual induction, then I can write the flux in terms of mutual induction. So in terms of mutual induction, phi 1 is it's M 21 I1 and 1 2 I2. That's equation number 7. So equating 6 and 7. So if I equate 6 and 7, then I will get M12 I2 is mu naught N1 N2 pi R1 square Li2. So I2 will cancel this I2. So it's M12 comes out to be, it's mu naught N1 N2 pi R1 square. So this is the mutual inductance of coil 1 with respect to coil 2, mu naught N1 N2 pi R1 square. Now, after M12, if he asks you to calculate M21, then can you tell me through which solenoid you will pass current? I'm asking you to calculate M21 now. S1, right, good. So you will pass current through S1, that's I1. So I'm just doing some very minor changes here. Instead of 2, you will get 1. I1 will pass through solenoid S1. This is S1, okay? So when it passes through S1, then you will have mu naught N1 I1. Then magnetic field B1 is mu naught N1 I1. That's my first equation. So if you look at this diagram very carefully, so this is your solenoid S, outer solenoid S2. This is your inner solenoid S1. You're passing current through S1. So whatever magnetic field you have, that is inside S1 only. Whatever magnetic field you have will be inside S1 only. So the magnetic field is only inside S1. There is no magnetic field through S2. So to calculate flux through each turn of S2, you need flux through each turn of S2. Then I represent it by phi 2 prime. And that is magnetic field of coil 1 multiplied by C. While calculating flux, we take area which is linked with magnetic field. The radius of the inner coil is R1 and that of outer coil is R2. See, this is the catch in this calculation. You need flux through S2. So you should have used the area of S2. But see, this is the area of S2. Just look at the diagram. Is the entire magnetic field is passing through the area of S2? Yes or no? See, this is your coil S2. The radius of S2 is R2. This is coil S1. The radius of S1 is R1. Magnetic field is within S1 only. So if I consider total area as S2, this is the total area of S2. This is this one. You can see very clearly that magnetic field is not passing through the total overall area of S2. Magnetic field is passing through only this portion of S2. See, this portion doesn't have any magnetic field. This is area of S2 but doesn't have any magnetic field. Magnetic field is linked with only this much portion. So while calculating flux, I cannot use pi R2 square because the area that we use here is the area which have magnetic field. But total pi R2 square doesn't have magnetic field. Only this much of portion of pi R2 square have magnetic field. So I cannot use pi R2 square because pi R2 square doesn't have whole of pi r2 square doesn't have magnetic field. Magnetic field is passing through only this much portion of r2. The radius of this portion is r1, so the area is pi r1 square. So this step is crucial. I'm repeating again. While calculating flux, we consider only that much area which is linked with magnetic field. The area of the outer coil is pi r2 square. But the whole of that area is not linked with magnetic field. Only this much of portion is linked with magnetic field. So I will not consider the complete pi r2 square. Rather, I will consider this much of portion which is pi r1 square. So we are still calculating flux through S2, but the area that we are using is pi r1 square. Next I call this as equation number 2. Total number of turns in S2. So just like S1, I can write that N2 as, this is N2 into L, that's equation number 3. So total flux linked with S2 is S2 is its phi 2, which is N2 into phi 2 prime. So your phi 2 is N2, which is N2L, multiplied by phi 2 prime, which is B1 pi R1 square. I call this as equation number 4, and this is 5. So I'm substituting 2 and 4 in 5. I'm substituting 2 and 3 in 4. So phi 2 is N2L into B1 pi R1 square, that's 5. That means this is flux through a single turn, one turn. And this is total flux with N2 turns. This dash means it's flux through one turn only. Okay, just substitute 1 in 5 and repeat all steps like we did in the previous case, and get the value of M21. Tell me how much is M21. So when you substitute these values and equate them all, you will get M21 is equal to mu naught N1 N2 pi R1 square. So M12 is exactly equal to M21. So this M12 is M21 is known as reciprocity theorem. And this happens always, not just for solenoid. You can have any coils. If you have a system of 2 coils of any shape and size, then M12 will exactly match with M21. Both the mutual inductance would be same. A solenoid of hint. The mutual induction is this mu naught N1 N2 pi R square. Remember one thing here, R is the radius of the inner solenoid. The solenoid having smaller radius is R1. N1, N2 are number of turns per unit length. And this is numerical take care of unit. Whenever you have centimeter square, convert this in meter square. These are the standard conversions. 1 centimeter square is 10 raised per minus 4 meter square. 1 centimeter is 10 raised to the power minus 2 meter. See here, the expression of M is, it's mu naught N1 N2 pi R1 square L. So your N1 is this. Yes, it's compulsory to substitute the value of mu naught. Your N1 is 25. N2 is, this is 25 per centimeter. You have to convert this in meter. So your N1 is 25 per centimeter. That means N1 is 25 by 1 centimeter. Now you can convert this 1 centimeter into meter. So it will be 25 by 10 raised to the power minus 2. I can take this 10 raised to the power minus 2 to the numerator. And this comes out to be 25 into 10 raised to the power 2 per meter. Similarly, the value of N2 is 20 per centimeter. So that you can write 20 by 1 centimeter, which is 20 by 10 raised to the power minus 2 meter. Your N2 comes out to be 20 into 10 raised to the power 2 meter. Your pi r1 square, the area is this. This area, this 25 centimeter square. It's 25 into 10 raised power minus 4 meter square. And the length is this, it's 20 turns. Sorry. Length is 50 centimeter. 0.5 meter. So if I substitute all values here, then I will get that mutual induction is mu naught, which is 4 pi into 10 raised to the power minus 7 into N1. N1 is 25 into 10 raised power 2. Then you have N2, which is 20 into 10 raised power 2. Multiplied by pi r1 square, which is 25 into 10 raised to the power minus 4, multiplied by L. The length is 0.5 meter. So the mutual induction comes out to be this 2, 2 and minus 4 would be 1. And this much of Henry. You can multiply these terms. So the next question on mutual induction is just like derivation. So you have two coils. These are not solenoid, these are circular coils. So you have two circular coils. This is coil 1, this is coil 2. This is the radius of second coil and this is the radius of first coil. So for system of two concentric coils. So you have a system having two concentric coils, one coil 1, another coil 2. Calculate mutual induction. Calculate mutual induction of coil 1 with respect to 2. So what's the name of this mutual induction? Is it M21 or M12? Mutual induction of coil 1 with respect to 2. That means M12. M21 means mutual inductance of 2 with respect to 1. 1 with respect to 2 is M12. Now tell me, current will pass through which coil? Through coil 1 or coil 2? So if you want to induce current in 1, if you want to induce EMF in 1, then current will pass through second coil, right? This is coil 1, this is coil 2. Okay, let's change this question now. If I ask you to calculate mutual induction of coil 2 with respect to coil 1, now tell me, through which coil current will pass? Good, current will pass through coil 1. So current is passing through I1. I1 will generate some magnetic field. Some flux will link with 2. Okay, one by one starts telling me. So I need magnetic field at center of coil 1. So in chapter number 1, we did magnetic field at the center of the circular coil. Do you remember the formula of magnetic field at the center of circular coil? Anyone? It's mu naught I1 over 2R1. That's magnetic field at the center of the circular coil. Now, through which coil you will calculate flux? You will calculate flux through coil 1 or you will calculate flux through coil 2. Very good. So if current will pass through coil 1, EMF will induce in 2. So flux we will take for 2. Flux through coil 2. Through coil 2, flux is simply magnetic field multiplied by area of coil 2, which is pi R2 square. You can easily substitute the values of 1 and 2. If I substitute 1 and 2, then you will get that phi 2 is B1, which is mu naught I1 by 2R1 into pi R2 square. So that's phi 2. Next, you can calculate this flux through mutual induction also. So using mutual induction, you can say that this flux is nothing but MI, where M is mutual induction, coefficient of mutual induction of coil 2 due to 1 into I1. In the next step, we will equate this 3 and 4. So when you equate 3 and 4, you will get that M21 I1 is mu naught I1 by 2R1 into pi R2 square. So I1 will cancel this I1. So this M21 comes out to be mu naught pi R2 square by 2R1. This is M2. So that was about mutual induction. After mutual induction, the next thing is self-induction. So in mutual induction, you have two coils. In one coil, current change, and in another coil, EMF is induced. But when we do self-induction, in self-induction, we have just one coil. In that single coil, flux changes, and in that coil only, EMF is induced. So when current in a coil change, then an EMF is induced in it, which oppose change in current through itself. This is mutual induction. So whenever current in a coil change, an EMF is induced in the same coil, which oppose any change in the strength of current. This is known as self-induction. This is known as self-induction. So self-induction is also known as inertia of electricity. This is also known as inertia of electricity. It plays the roles of inertia in current. It plays the role of inertia in current. So what this statement means, if you have a coil, there's just one coil. I don't have any other coil, I just have one coil. This is key. As I close this key, so current in this coil will increase. So when current increase, the flux linked with this coil will increase. So due to increase in flux, this coil will induce an EMF in itself. It's not inducing EMF in another coil. This is inducing EMF in itself. And it will induce a current in itself if your circuit is closed. This phenomena is known as self-induction. So it's opposing the current of itself. It's not opposing the current of another coil. This is inducing a current itself to oppose its own current. I is opposing its own current. That's why we call this as self-induction. Is it clear, the phenomena? Here this induced current is not opposing the current of the neighboring coil. It's opposing the current of the same coil. It's opposing its own current. That's self-induction. And it's a very common phenomenon. Wherever you have a coil, you will have self-induction. For mutual induction, you need a second coil. But for same coil, so if you have one more coil near to it, then along with self-induction, you will also have mutual induction. So you will have both self as well as mutual. But if you have just one coil, then you will have self-induction. So flux linked with the coil phi is directly proportional to the current through the coil. If I remove the sign of proportionality, I will use a constant L and this phi will be equal to Li. So this phi is equal to Li. This L here is coefficient of self-induction. This L here is coefficient of self-induction. This L is the coefficient of self-induction. So just like mutual induction, you have a coefficient of self-induction. So if your system have n turns, you can write your n phi is equal to Li. So you have this thing, n phi is Li. So using Faraday's law, so if I use Faraday's law here, induced EMF E is minus of d over dt of n phi. It's minus of d over dt of Li. Your induced EMF is minus of L di over dt. This is induced EMF minus L di over dt. This is induced EMF. And this negative sign, as ever, it shows Lenz's law. So if you don't want direction, then you can take mod of E is L di over dt. Or you can write your L as its mod of E over di over dt. So that's self-induction. L is mod of E over di over dt. Now, if I take units, if I take SI unit of L. So SI unit of L is volt divided by current, which is ampere, divided by di over dt is ampere per second. You can take this second in the numerator. It will be volt per ampere seconds, and that we call Henry. So SI unit is Henry. So both mutual as well as self-induction, the SI unit is Henry. For both unit is Henry. Then you can get a 1 marker question to define 1 Henry. Define 1 Henry. You can get this question to define 1 Henry. So to define 1 Henry, we start with this equation. L is mod of E over di over dt. What is di over dt? Di over dt is rate of change of current. So for 1 Henry, if rate of change of current through a circuit is 1 ampere per second. The rate of change of current through a circuit is or through a coil is 1 ampere per second. And due to this rate of change of current, if induced EMF is 1 volt. So if rate of change of current is 1 ampere per second, and due to this rate of change of current, 1 volt of EMF is induced in the coil, then self-induction is 1 by 1, that's 1 Henry. So you can state this as if rate of change of current of 1 ampere per second induce an EMF of 1 volt, then self-induction is 1 Henry. So you may get this definition, that's what's 1 Henry. 1 Henry means if rate of change of current of 1 ampere per second induces an EMF of 1 volt, then the self-induction of that coil or that circuit is 1 Henry. Sure. So next you can get conceptual question like tell the parameters which can affect the self-induction. So self-induction of coil depends on first number of turns and after number of turns it also depends on area of cross section. It also depends on area of cross section A. Now along with area of cross section it also depends on the nature of material, the nature of medium in the coil. So these are the factors which can affect the self-induction of a coil. So the next is self-induction of a solenoid. Okay, let's do one thing. In this derivation, I will tell you the steps, but I will not do calculations. You will do calculations and then tell me the final result. Self-induction of solenoid. I'm telling you the steps, but you will do the calculations. So you have a solenoid. Solenoid is, the radius of each turn is R. So R1 is radius of solenoid. Second, N number of turns per unit length. Number of turns per unit length. L is length of solenoid. L is the length of solenoid. Some current is I is passing through the solenoid. I is current through the solenoid. Okay, I'm telling you the steps. In the first step, calculate magnetic field to the solenoid. In the second step, calculate flux through each turn. Flux through each turn. In the third step, calculate total flux. In the fourth step, calculate that flux using Li. In the fifth step, equate 3 and 4 and get the value of L. You will first need magnetic field due to solenoid. So the magnetic field due to solenoid is this, B is mu naught Ni. That's first equation. Now you will need flux through each turn. You need flux through each turn. So flux through each turn is phi prime, which is magnetic field multiplied by area, which is pi r square. So that's equation number 2. You can substitute 1 in 2. When you substitute 1 in 2, then your phi prime is, it's mu naught Ni into pi r square. So that's your phi prime. That's equation number 3. Now this is flux through each turn. Next, I need total number of turns. So the total number of turns are represented by capital N, that's number of turns per unit length into length. So that's equation number 4. So for total flux through solenoid, it's total number of turns multiplied by flux through each turn. So this is NL multiplied by mu naught Ni pi r square. So the total flux comes out to be mu naught pi r square N square Li. That's equation number 5. So if L is self-induction, then your phi would be Li. You can equate 5 and 6. So when you would equate 5 and 6, you will get Li is mu naught pi r square N square I. So I will cancel this I. You will get L, which is mu naught pi r square N square. That's self-induction. So this is the self-induction of the solenoid, mu naught pi r square N square. Now, instead of this solenoid, you can get a circular coil. So the question could be, calculate magnetic field, not magnetic, calculate self-induction of a circular coil having n turns and radius is r. Or try to solve it without any hint. So this is your coil. The radius of the coil is capital R. You're supposed to calculate the self-induction of this coil. Magnetic field at the center of the circle is this, mu naught I by 2R. If it have one turn, but if have n turns, then multiply it with it. See, if I calculate magnetic field, then magnetic field is mu naught Ni over 2R. Next, I need flux through each turn. Flux through each turn. So flux through each turn is just phi prime, which is magnetic field multiplied by area of the coil, that's pi r square. So if I multiply it here, it comes out to be phi prime is B, which is mu naught Ni over 2R into pi r square. So the square will cancel this R. Phi prime comes out to be mu naught Ni pi r by 2. Then total number of turns are N. So N are total number of turns. So you can easily calculate total flux. Total flux phi is N phi prime. So total flux phi is N into mu naught Ni pi r by 2. Yes, Jabana, that was I was asking you. You didn't take area. So this phi is mu naught N square pi r I by 2. That's my equation number 1. Next, I can write this as phi is equal to Li. That's equation number 2. I can equate both of them. I can easily equate them. I can equate 1 and 2. So if I equate them, then my phi is, okay, so if I equate them, then your Li is mu naught n square pi r square I by 2. So this I gets cancelled out with this I, your L comes out to be mu naught n square pi r by 2. So this is the coefficient of self-induction of a circular coil. So instead of circular coil, you can get any shape. So first of all, you will calculate the magnetic field due to that shape, and then after the magnetic field, you will calculate flux and equate that flux with Li.